Hello minions, welcome back to Nick Does Maths. We're going to do some probability and geometry at the same time. Oh no! Let's give it a go. We've got a circle centre 0. Its radius is x, but x is an instance, a random observation of the random variable x, which belongs to the uniform or rectangular distribution between 0 and pi. So that means it's equally likely to take any continuous value between 0 and pi. Find the probability that the area of the circle is greater than 10 centimeters squared. We're then going to talk, is the median area of that circle bigger or less than 10, do we think? And then we're going to do something to do with a triangle. So, okay. We've got our circle. Its radius is x. What is its area? Well, the area of the circle is pi r squared, so pi x squared. So we want the probability that that area is less than 10, i.e. we want the probability, you know what, let's do that here. We want the probability that x squared is less than 10 over pi, which is the probability that x is less than root 10 over root pi. I am aware that this is a quadratic inequality, but because x is a length, it's a measurement of a length, it is positive. X is only ever between 0 and pi. Okay, so I can just square root everything nice and easy. Now, because we're in the uniform distribution, right, what we're saying is x can take any value from here to here. So what we want is, where's my red pen? The probability that it was greater than 10, wasn't it? Greater than 10. Bosh, bosh, bosh. We want that length as a proportion of the entire length. So that is going to be pi minus root 10 over pi, which is that distance there. And divide that by the total length pi, and that gives me, to the calculator, pi minus square root of 10 over pi, whole thing over pi, 0.432. Channeling our inner BBC Radio 4. Okay, step 1 completed. Now, that does also give us largely the gives us the answer to B. And actually my number line here is quite a nice way of doing it. So we know that the probability of landing in here is 0.432. That's my probability right there. Now the median would have a probability of a half. All right, you should have 50% above, 50% below. That's the whole idea of a median. So what does that mean? Well, quite obviously, right, you need a higher probability. All right, you need a higher probability, 0.5. So that number there needs to scoot lower. Okay, so that tells me, B, that the median has to be less than 10. Okay, because I want a higher probability, so the median has to be less than 10. Okay, I want more probability. Median has to be less than 10 as the probability that the area is bigger than 10 is less than a half. There we go. That's a good justification. All right, now, what's going to happen? We're going to take two of these radii, OA and OB are radii. Angle AOB is x. The radius is x. These are all still the same instance, or they're all generated from that random variable. We want the area of, so we want the expected value, as this pen has died, of the triangle OAB. So first of all, what is the area of triangle OAB? Well, it's half x squared sine x. Half AB sine C. Nice and easy. Next, we need to do the expected value. Now, we are on a continuous random variable. We're on a continuous random variable. My PDF for x, what is the PDF for x? Well, it's just 1 over pi, the uniform distribution. All right, think of it as the probability of any given value is 1 over the length of the interval that we're on, 1 over pi. So what do I need to do? Well, it's integration. The expected value for the area is is the integral of the thing I want the expected value of times 1 over pi dx, and x can go from 0 to pi. Now that is 1 over 2 pi, just tidy this up a little bit, x squared sine x dx. Now, this is going to be integration by parts, multiple times, because I've got this polynomial x squared, which every time I differentiate will get smaller, and then I can keep integrating the sine x. That's not going to make a huge difference for me. I'm going to use this little method here. It's a nice way to do integration by parts multiple times. This is the differentiating column. This is the integrating column. All right, so let's keep differentiating x squared. I get 2x, then I get 2, then I get 0. Sine x, I'll get minus cos x, I'll get minus sine x, and I will get cos x. Don't know why I'm still clutching the red pen. It doesn't work. Now, what do we want? If you haven't seen this algorithmic sort of layout before, all it is just doing integration by parts for us, and it's keeping track of a few things. That's all it is. You can try it out. It does all the stuff. And we want these diagonal terms. All right, we want these diagonal terms, and we pick up alternating signs. And again, this just comes from the definition of integration by parts. Check out that it works for yourself. So my expected value is 1 over 2 pi of minus x squared cos x plus minus 2x sine x plus 2 cos x, and I need to plug in 0 to pi. Is that going to do anything nice for me? Let's plug in pi. Cos pi is minus 1 with a minus, so I end up with pi squared. Sine pi disappears. Bye-bye. 2 cos pi, so that's a minus 2. Let's plug in the zeros. That will do nothing for 0. That will do nothing for 0. And I get another minus 2. So what do I end up with as a expected value for the area of this circle? 1 over 2 pi, area of this triangle, pi squared minus 4. Whatever that is. Do you know what? Why not? Let's watch Nick do calculator. Pi squared minus 4 over 2 times pi. Sure. Yep, apparently, that number, I know you're all dying to know, cliffhanger, 0.934 centimeters squared. Et voila. Okay, a lot going on. I just thought I'd demonstrate how we can do these calculations, taking one random variable like the uniform distribution and expanding that up to other things, like using that to find the property of certain areas, certain shapes, and things like that. You can do some really, really cool things adapting the uniform distribution with numerical simulations, things like that, using very similar ideas to this. Look it up. There's a great way of just numerically simulating the value of pi using random, just instances of random numbers like that. Look it up. Tell me about it. Okay. Don't forget to subscribe and hit notifications so that you don't miss the next one of these. Should be coming out in the next couple of days. I hope you found this interesting. I'm Nick. I'll see you next time, minions.